Yes, sir, you may start.
So my screen is visible to you, I hope. So with this, good morning to all of you. What we discussed in the last class was factors governing selection of source of water. On what basis we can choose a particular type of source of water for the water supply scheme which we are planning. Now, next immediately we'll be talking about the underground water or the subsurface water. Now, to define it, I would say all water beneath the land surface is referred to as underground water or subsurface water. So the equivalent term for water on the land surface is surface water, which we have discussed before. Underground water occurs in two different zones. Fine. So you can see here in this particular diagram, in this schematic diagram, and when I speak, if you concentrate on this particular schematic diagram, you can understand better about what I am talking. Now, so there are two different zones which come under this underground water. So the first one is zone 1, which occurs immediately below the land surface in most areas, and it contains water and air both. And this is the area which is, as far as moisture state is concerned, it is in unsaturated state, and that is why this particular zone is referred to as the unsaturated zone. Now, the unsaturated zone is almost invariably underlain by a zone in which all the interconnected openings are full of water, and this zone is referred to as the saturated zone. So in this case, if you see, I'll just try to show you, to laser point. Now, this is the zone which is, at the groundwater, the groundwater table exists in that particular level, so which is written as water level, and whatever is existing beneath that, this is absolutely saturated. Immediately after the groundwater table, depending upon what kind of stratum or what kind of formation we have, there will be a certain zone where, because of the capillary fringe action, that particular zone will also be saturated, but because of the effect of capillarity. So continuing from that zone to the beneath zone is known as saturated zone, which has been marked in the left hand side. On the other hand, the unsaturated zone, which I talked about before, is mentioned, in its own over here at the top. So we have the surface, and then immediately after that we have that unsaturated zone. Now, water in the saturated zone is the only underground water that is available to supply wells and springs, and is the only water to which the name groundwater is correctly applied. Fine. Recharge of the saturated zone occurs by percolation of water from the land surface through the unsaturated zone during the time of precipitation. Now, the unsaturated zone is therefore a great importance in groundwater hydrology in many sense, and for as a geotechnical aspect, if you want to consider, this zone of unsaturation has huge role to play in the overall strength and stability of the soil. Now again, if you see, this unsaturated zone can be divided into three parts, which have been shown over here in this diagram. The first one is the soil zone, which is immediately just beneath the surface. After that we have an intermediate zone, and then the upper part of the capillary fringe is the another one zone. So the soil zone extends from the land surface to a maximum depth of a meter or two, and in this, and is the zone that supports plant growth. So mostly root growth and root migration would occur in this particular zone. Now, Since all these roots, all this worms and other microorganisms, other vegetations, animals, worms, they live and survive in this zone, so automatically the porosity and permeability of the zone tend to be higher than the underlying material, and the soil zone underlain by the intermediate zone, which differs in thickness from place to place depending on the thickness of the soil zone and the depth of the capillary fringe. So there are several characteristics of the soil which has to be considered before defining these zones. However, all these zones exist for any type of soil which you take. Now, the lowest part of the unsaturated zone is occupied by the capillary fringe. So here also you have capillary action going on, but that is not that strong, so that it can make the entire soil layer saturated. That is why this is an unsaturation zone which has happened because of the capillarity. So the capillary fringe results from the attraction between water and rocks, and as a result of this attraction, water clings as a film on the surface of the rock particles and rises in small diameter pores against the pull of gravity. Fine. So if you see, water in the capillary fringe and in the overlying part of the unsaturated zone is under a negative hydraulic pressure. Fine. And that is, it is under a pressure less than the atmospheric pressure or the barometric pressure, because of the suction, water is getting up now, and going opposite to the gravity. Now the water table is the level in the saturated zone at which the hydraulic pressure is equal to the atmospheric pressure, and this is very important to remember, right? So with this, I'll move to different formations which we usually talk about, and they act as the different sources of groundwater. So the first one is aquifer. So aquifer is a word which was produced, basically from the Latin. So aqua means the water, and fair means which can bear the water. So therefore, the term aquifer can literally be understood as water-bearing formation. Fine. So it can formally be defined as a saturated permeable geological unit that is permeable enough to yield economic quantities of water to wells. Now, there are several situations which may happen, and I will be discussing subsequently. Now here the most important characteristics of this particular formation is that it has the properties by which yielding of water through the well is economic. That means the energy which you are spending is less compared to the water which you are getting. That is very important to remember. In other words, it is defined as the saturated geological unit that can transmit significant quantities of water under hydraulic head. Hello, am I audible? Am I audible? Hello?
Yes, sir.
Okay, thank you. Yeah, so we are talking about aquifer. So the thing is, saturated. In other words, I defined it as the saturated geological unit that can transmit significant quantities of water under hydraulic head. So the most important underground water-bearing materials are unconsolidated sand and gravels, but permeable sedimentary rocks such as sandstone and limestone and heavily fractured or weathered volcanic and crystalline rocks can also be taken as the aquifer and would have the capacity to bear the water. So, this is the way aquifer is defined. Next, the another type of situation, and based on that, we have different type of formation, and that is what is known as aquitard. Now, let me explain you the situation where, you know, in a geological unit that is permeable enough to transmit water in significant quantities for large area and long period. But its permeability is not that sufficient to justify the construction or production of wells to be placed into it. So that means, still it has the capacity to transmit water from one point to another point, throughout the prolonged period of time, and then the quantities can be significant. However, in short term, where in case of, which is conducive to construct wells, in those cases, in short term period, the permeability is not that significant that so much water would accumulate in a short period of time, and which can be yielded out by construction of wells. So that is not possible in case of aquitard. Aquitard is a geologic formation that can transmit water at a relatively lower rate compared to the aquifer. That is pretty much obvious, that though it has the transmissibility properties, but it is quite lesser compared to the aquifer. And if we talk about the examples of aquicludes, so predominantly clays, loams, shales, these are the type of formation where you can see aquitard. You know, Next is aquiclude. So aquiclude is an impermeable geologic unit, so which does not transmit water at all. So in this case, we do not have properties to transmit water from one point to another point within the formation. Although this formation is capable of absorbing water slowly, it means that this geological formation can store water, but it cannot be transmitted so easily. Fine. In different way, we can say aquiclude is a saturated geological unit that is incapable of transmitting significant quantities of water under ordinary hydraulic head. So usually when we give example, we talk about metamorphic rocks, but not all metamorphic rocks are aquiclude. Depends upon several other factors, which we are not going to talk about here. And next comes the aquifuse. So this is a geological formation which does not absorb at the same time, and it does not transmit also. So this is the uh, portion is also very much important. So four different situations can happen, and because of that, we have renamed four different formations which are usually available while talking about the source of groundwater. Now we'll be talking about the types of aquifer. So first one, obviously unconfined aquifer. So in this case, yeah. So basically, if you see in the right hand side figure first, it is better to understand from here. Now, an unconfined aquifer is an aquifer which is bounded by aquiclude at its lower side and by water table at its upper side. So in other words, in the upper part of the aquifer is not restricted by any confining layer, and that is why we say it is unconfined aquifer. And that makes the upper part a bounded free surface. Now, consequently, the free surface of unconfined aquifer is under atmospheric pressure, and its upper boundary is water table, usually, which is free to rise and fall depending upon other factors. Rate of percolation, rate of precipitation. Those are the factors on which the rise and fall of the water table depends upon. So basically, we can say that depends on the seasonal variation as well. Now, unconfined aquifer is directly recharged by filtration. So in a single formation here, if I would like to show you, in a single formation you can see both type of aquifer. So unconfined aquifer I have not discussed yet, but when I discuss in the next slide, you will be able to understand that in a single formation we can have both type of aquifer, unconfined and confined aquifer. So in this case, this part and these parts are unconfined aquifer, since the top portion is basically the water table. It may come up to here, but still then the top boundary is water table, and we have no impermeable boundary which is confining the upper boundary of the aquifer. That is what is known as unconfined aquifer. Here also you can see, and these are the nomenclatures which are usually used in order to calculate the yield of the unconfined aquifer or confined aquifer. So ACE is actually stands for drawdown. We have H, water level after pumping. Capital H is the water level before pumping. That is the static head, the height of the water table. R is the influence area of the radius of the influence area, and then R is the radial distance. So these nomenclatures are quite standard. That is the reason I have provided over there. Now comes the confined aquifer. From the figure which I have shown in the previous slide, you can understand that a confined aquifer is an aquifer which is bounded by an aquiclude both at the lower and the upper part. In other words, we can say that it is basically sandwiched between two aquiclude. Fine. So this aquifer is confined between two impervious layer. If I say based on the physical phenomena. So the confined aquifer is known as pressure aquifer, and in a confined aquifer, the pressure of water is usually higher than the atmospheric pressure, since it is sandwiched between between two impervious layer. The water in a well which is constructed in such an aquifer rise usually above the aquifer and even above the ground surface due to high pressure. So if it would have been as per the atmospheric pressure, then the water would not have come to the top. However, since in confined aquifer, water usually remains in more than atmospheric pressure or higher than atmospheric pressure. So if you construct a well, or if there is a well which there is a natural formation like springs gets created, the water will automatically come and it may go above the ground surface due to the high pressure. So the ground pressure can either be equal or greater than the atmospheric pressure, and confined aquifer cannot be recharged directly by infiltration. So you should be able to understand that confined aquifer cannot be recharged directly. There has to be some connection with an unconfined aquifer, and through which confined aquifer can get recharged. So the next immediate one is a very interesting formation we are going to talk about. So that is the parched aquifer. So basically, parched aquifer, what happens is there will be a layer. You have an unconfined aquifer, and you have that groundwater table. So the groundwater table is the upper boundary of an unconfined aquifer. What happens sometimes, if we see that there is a layer between, layer between the groundwater table and the top surface, which we discussed in the beginning of today's class. So in that particular layer, if we have some, you can see the shape which I have shown over here, and if we have such kind of formation which is impermeable, or which is made up of aquiclude formation, so in that case what happens is, because of the percolation of the water, there might be water accumulation at the top of that particular aquifer. Now, since this is isolated, this is parched from in the original water table and original unconfined aquifer, this is called as parched aquifer. And often what happens is you construct a well and you get water level very early than which you are expecting, and often we misunderstood this, thinking that our original water table is over there. But however, the accumulation of water in these aquifers are not huge. So that is why you can observe that the entire water present in the parched aquifer can get exhausted quickly, and that is why that can create a problem. So whenever we try to construct well which will be used to provide water in the water supply scheme, we should be ensuring one fact, that we have not constructed the well up to the parched aquifer. It has to go to the minimum to the unconfined aquifer or confined aquifer, depending upon what sort of formation we have. So next, another one interesting aquifer is leaky aquifer. So you can see the main difference in leaky aquifer. We have aquitard, and we have exclusively aquitard. So we are not going to talk about here about aquiclude or aquifuse. We are talking about aquitard. You might have while discussing, you might have realized that aquifer has the capacity to store water. So a leaky aquifer is also known as semi-confined aquifer, as either both the upper and the lower boundaries are aquitards, or one of them is aquiclude, another one is aquitard. So one of them has to be aquitard, and the water is free to move through the aquitards either upward or downward. So though there is no horizontal movement through the aquitard, but water can go up and down because it has the capacity to store water, and often that is what is known as leaky aquifer. So usually these are the different type of water formation from which we can get water. Now we'll be talking about few important physical properties on which the amount of water which we collect depends upon. So the first one is obviously the porosity, and all of you know that the voids with the ratio of the openings to the total volume of the soil or rock is known as the porosity. Volume of void by total volume. Right? You might have studied this definition in geotechnical engineering or soil mechanics 1. Now porosity is expressed either as decimal fraction or percentage, and so porosity is the most predominant parameters on which this movement of water depends upon, and all those formations which we discussed before depends upon the porosity. While defining them also, we discussed about the variation in their porosity characteristic. Right? So the porosity is usually expressed as a percentage, and the porosity values taken in the range of 0 to 1 based on the geometrical formation, and it indicates the capability of the medium to store water. And that's the main important part. In other words, it measures water bearing capacity. Therefore, the total potential of groundwater can be calculated by using the expression. You can see over here, Vp is equal to time to Va. So Vp is the potential groundwater, and Va is the volume of the entire volume of the aquifer, and Eta is the porosity. Now, one important point: not all the water found in the pore space can be extracted, as some of the water will remain in the void space because of the surface tension forces. So this is also very important. There are different type of waters which are present in the water, in the soil, or in the formation. So all type of waters cannot be taken out. So we only can take care of the free water part. So a few portion of the water will remain over there because of the surface tension, which is very difficult to take out by the force which are usually applied to yield the water from the groundwater sources. So you can see over here, so just pictorially, since we are now discussing everything in online, to give a to put all the statements into perspective, I thought of putting this figure over here. So we have volume of void and we have the total volume, and so total it's the volume of void which is actually within the total volume itself, and in the right hand side we have shown that, and then the porosity is 0.3 by 1, so 0.3 is the porosity. So this is a very I would say helpful for understanding the porosity which we are talking about here. Next is specific yield and specific retention. This is also very important, the specific yield and specific retention, because you know, they are the most important factors while talking about mm, physical properties of the formation. So what is specific yield? So specific yield is the volume of the groundwater extracted by the gravity drainage from a saturated water bearing material, and is known as the yield. And when it is expressed as the ratio of the volume of the total material drained, then it is known as the specific yield. So specific yield is the volume of water obtained by gravity drainage by the total volume of the material drained or dewatered into 100. On the other hand, specific retention or field capacity. So specific retention is often called as field capacity. So in this case, the quantity of water retained by the material against the pull of the gravity is termed as the specific retention or the field capacity. And this is also expressed as percentage of the total volume of the material drained. Now, specific retention or field capacity, it will have the similar kind of numerical definition: volume of water which is held against the gravity drainage by the total volume of the material, into 100. So it is evident that the sum of the specific yield and the specific retention is equal to its porosity. So that is the important part and should be remembered. So here again we have that diagram. Chemically we are trying to show you. So the specific retention is basically the which has got arrested within the matrix of the soil, and specific yield which has come out because of the gravity. Now porosity is basically the water which has come out plus the water which is already present, so that entire would give us the porosity. So that is why porosity is specific yield plus specific retention, and we have already defined how to calculate specific yield and how to calculate specific retention, and we get the same value which we previously obtained. So now we are going to talk about very important part. This is where there is a difference in the understanding of a hydraulic engineer and soil, or a geotechnical engineer. So the main difference lies in that how to define the hydraulic conductivity and permeability. So the hydraulic conductivity is constant of the proportionality in Darcy's law. Most of you have studied this. It's simple, and it is defined as the volume of water that moves through the porous medium in unit time under the unit hydraulic gradient. So that is what is the hydraulic conductivity. So hydraulic conductivity has a dimension length per time, which is also very obvious and function of properties of both the porous medium and fluid. So this is very important to remember. When we talk about hydraulic gradient, we talk about, basically we say that hydraulic gradient depends upon the factors which is related to the porous medium as well as the fluid which we are talking about. And horizontal hydraulic gradient is hydraulic conductivity is approximately 3 times greater than the vertical hydraulic conductivity based on the formation of the porous medium. On the other hand, permeability is solely used in case of geotechnical engineering, and since in this case water is a standard material to be considered, so that is why in this case we don't talk about the properties of the fluid. Rather, while talking about permeability, we basically talk about the properties depends upon the porous medium only. So that is the main fundamental difference between these two. Okay, now another one very important term, that is the transmissibility. Now transmissibility is the, it is introduced by Thies. Now Thies has derived all sorts of different equation. Employing them, you can basically calculate the yield of a well which is situated in an unconfined aquifer. Similarly, for confined aquifer, for different situation of wells, you can calculate the overall yield by help of this equation. So this is a very renowned researcher and scientist, we can say, and so coefficient of transmissibility, or transmissibility of soil, which is defined as the rate of flow of water through a vertical strip of the water bearing material, usually aquifer, of unit width and full depth under a unique hydraulic gradient and at a temperature of 20 degree. Now the relation between K and T is given over here. So T is equal to K into D, right? T is equal to K into D. What is K? So basically this is measurement of the amount of water that can be transmitted horizontally by a full saturated thickness of aquifer, right? Understood? Now tell me, I have asked you one question. What is K? Capital K. Who is going to answer me? Anyway, so basically, you people are silent, and that's what actually I was telling in yesterday's get together also. We should speak. So K is the coefficient of permeability. Usually, in conventional way also, we denote K as a standard connotation, and T is always the transmissibility. So now is the next one is the intakes for collecting surface water. So this is the new one which we are going to discuss, and in this case what is important is how to collect the water, what are the different structures available by which facilitate the collection of the water from the source. So that is the so the main function of the intakes works is to collect water from the surface source and then discharge water so collected by means of pumps or directly to the treatment plant. So so the main task of intakes are basically to collect it from the surface, so collect it from the source and then send it to the treatment plant. Intakes are structures, obviously, which essentially consist of opening, grating, or strainer through which the raw water from the river, canal, or reservoir enters and carried to the pump, carried to the sump well by means of conducts or any sorts of conduits. From the sump well, again it is pumped through the rising mains of the treatment plant. So this is you should be able to imagine how the entire process would look like. Now there are a few points regarding the intake of any sites, and we should be considering them. Now let me talk about them. So where the best quality of water is available so that the water is purified economically in less time, so that part has to be decided exactly among different surface water source. When you choose a particular source, so in that source also there might be different point where you will get the most purified water, and in that particular point if you construct your intake, then the overall treatment would be more economical. At site there should not be heavy current of water, obviously, then that will increase the turbidity of the water, you know very well by now, and which may damage the intake structures as well. So there are two things, if you have a huge amount of current, so obviously, so one is the structural aspect, and as far as the quality of water is concerned, then also the treatment, the cost for the treatment would also increase. Now the intake can draw sufficient quantity of water even in washed conditions. So this is very, very important. During the when the discharge in the source is minimum, then also you have to ensure that your intake structures is able to draw the water during maybe hot summer days. So This, that is the worst condition which we consider. Now the site of the work should be easily approachable without any obstruction, and so you have to create your intake structures in a place which is easily accessible. So if there is an issue or if there is a problem in the operation, immediately you should be able to take care of that. Now the site should not be located in navigation channels, so this is very very important. So it has to be away from the navigation channels, because navigation channels has several complications, in terms of current, in terms of turbidity. So we try to keep these intake structures not in the navigation channels. As far as possible, the intake structures should be near the treatment plant, so that the conveyance cost is reduced from source to the water treatment plants. So these are the very I would say tricky things, and that significantly influences the overall cost of the project. Now at the same time, we have to take care of the fact that the intakes would not be located in the vicinity of the point of the sewage disposal for avoiding the pollution of water or contamination of water. So that's what I was talking about. Even if you choose a particular water body, and in the vicinity of that, there might be several points where you will get the most purified water, and there will be several points where you will get the highly polluted or highly contaminated water. So that part should be taken care and should be observed critically before planning a particular site for construction of the intake structures. Now at the site, sufficient quantity should be available for the future expansion of the water works. So that is also, as I have already mentioned, that always we should have the provision to increase the capacity or creating some extra facilities. So that is why we need to take care of that part also, so that in future, if we want to increase the number of intake structures, we should have that provision. So that part also should be planned beforehand, and before you start constructing the intake structures. So with this, we'll stop today, and the different type of intake structures we'll discuss in the next class.